always, but I don't know.
I found it anyway. It looks like it's recording now. So
Yeah. Okay, cool.
cool. And it's by fast, so we can start, I guess. I'll share my screen. Cool. Can everyone see that? Okay. Yep. Okay, cool.
Yes.
Yeah, so I'm going to give a talk on containerized applications on the HPC. I just have like a little presentation first with some like background, and then we'll like go through some examples basically. That's how I'm going to do it. If you have any like questions during it, it's fine to just ask questions or interrupt. It should be interactive, I think. Okay. So I guess to start, I want to know how many people are familiar with the HPC. Has anyone here used it before? Yeah, you can see some hands up. I only ask that just as if you don't know anything about the HPC, I can spend a little bit more time going through some of the basics, but maybe some of the stuff will be a little more advanced. And so something maybe you can come back to after you've learned a little bit more, but I'll go through some of the things to start with anyway. So this is kind of what it looks like to use the HPC. You SSH into a computer at JCU and access a terminal node. There's a slightly more interactive way to do this, which I'll try and show today as well. But basically, you work through a terminal, and it's not on your computer, right? Like you're using the computing resources elsewhere to do your computation. But you can access it basically as if you had a very long HDMI cable or something like that connecting your screen to another computer. So this is sort of what the layout of the high performance research computing cluster at JCU is. You would be here on your laptop or PC or whatever, and you'd SSH to the Zodiac address, and you get load balanced onto one of these login nodes. Their login nodes are pretty powerful. They have a bunch of cores, a lot of RAM, and hard drive space. And so you'll end up on one of these. You can move between them pretty easily. They're called LN01 and LN02. And basically the idea is that you sort of access these nodes and then use the qsub command or qsubmit command to send jobs to the large compute resources that are on the HPC. So there are basically equivalent to the login nodes, but many of them, 40 cores, similar CPUs with lots of RAM, and there's also a couple of GPU nodes as well. So you can access them if you need to do something that requires GPUs, so like image manipulation or like long read based cooling, I guess today is using a lot of GPU stuff. So that's the basic layout. There's a server and a scheduler for PBS that sort of organizes how the stuff gets put on the nodes. But that's just sort of a basic layout of the HPC. So really what I want to talk about today is package management on the HPC. So it is a managed system. When you arrive at this, it's like highly orchestrated. It's, there is a person who runs, maintains and runs the HPC. So it's just not a free-for-all. There are rules and stuff that you have to abide by. And one of the things is that there's a shared module system for the packages that are available on the HPC. There's, I think, kind of two flavors. Like there's the module system, the Linux system, and the Conda environment system that contain different applications, basically. So there's over 300 packages. They're shared between all users, and there's a administrator in charge of updating these. So it's sort of one person's job. If you need an updated package or a different version of a package, you have to let them know, and they can install it. So it can lead to a slow update process. And just for like a little example, I just went through some of the packages that I've seen before and checked their latest versions. And so all the ones in red are out of date. They might just be like a minor version out of date, but some are major versions and some are, yeah, secondary minor versions. But it can be pretty hard to keep things up to date when one person is sort of in charge of it. And there can be this sort of conflicting problem of like, everyone has to share these. So if one person wants to use Minimap, you have to start specifying every version of Minimap so that there isn't conflict if there's breaking changes in the system. So this is where containers sort of come in. So containers are a platform that allow you to create and run container platforms, right? Allow you to create and run containers that package up pieces of software in a way that is portable and reproducible. So what does that mean? It basically takes, you have an application and it takes all the dependencies of that application and puts it into one file or into a series of files that allow you to run that application independent of other things on the computer. So independent of operating system or other pieces of software that clash, because everything is packaged up in one nice little container. They're different to a virtual machine. So you might know that like a virtual machine can do this. This is an example of a virtual machine where you virtualize the entire guest operating system. So you'll have a virtual operating system that runs the applications, and these are pretty heavy. So to virtualize an operating system, it's a lot of work. As opposed to containers, they're basically an isolated process. So they share the operating system. They use the operating systems or like features from the operating system. They share that together, but they are isolated in their like privileges and networking and things like this. So they're much lighter. So you can run lots of them. They have smaller packages than a VM, and they're pretty fast and portable to move around. So they're useful for using in research for packaging up and sharing containers and applications. So yeah, why would you use containers in research? So data reproducibility, you can sort of know how it's built the same way every time. Cross-system portability, you can run a container on my Mac, will run on a Windows, will run on a Linux, on the HPC this way. Simplified collaboration, you can just give a container to someone else and say, run this. This is my workflow. It's all there. It doesn't matter about what operating system they have. Yeah, you don't need to worry about complicated software dependencies of like, what did I install when? So you sort of define all that in your container to say like, this is all the software and the versions that are required to run this. Yeah, and if you're doing testing, it gives you a good consistent environment to know that things will always turn out the same. So this is a sort of a basic, some of the terminology, I guess, that's used in containers. This is for Docker. And so Docker is one of these container platforms, which is pretty popular. The one that's on the HPC is called Singularity. And it's been optimized to work on high performance computers. And it has some special features which make it really the ideal choice for using on HPC. And so that's already available to us, but they have very similar terminology. So basically there are these registries. And so they are basically, you can think of them as like a software store or something somewhere that holds all these repositories online, or it could be privately hosted on your premises, but generally you just use public cloud providers, and they hold the images of the containers. And so the images are static files, or static, basically static files. If you think of the example of like Photoshop, the files for Photoshop would be the image, and then the container itself would be when you open Photoshop and it's running and you're interacting with it. So a container is the image instance that's running an app, whereas the image itself is just the static files that say like, this is the app. So there's a little bit of terminology there, which can be confusing because you have to manage both your images and your container, your containers and your images, because you can sort of spawn multiple containers from a single image. But it's not too bad with Singularity because the images are a single file, so you can sort of just delete them as you would. And but yeah, if you're not doing anything too crazy, it is fairly easy to manage. So yeah, registries, images, containers. Yeah, so Singularity is one of these container platforms. It is, the the preferred container platform, HPC clusters, you don't need root access to run these containers, and you can manage the containers yourself. So you can install and change, update containers in your home directory by yourself. So it's on the HPC. This is what like the Singularity help command highly is container platform optimized for high performance computing. Right? So it is definitely the thing to be using on the HPC. Just to go over some basic commands before we jump into some examples. The sort of standard workflow that you'll do is you'll find a container on one of these repository stores. So Key or Docker Hub are good places to look for containers. And so basically these are just pre-built software packages. So generally all the major software applications that have a release cycle will generally release a container image nowadays as well. So you can just sort of go onto Docker Hub or somewhere, find one that has a lot of stars, and then pull that container basically. So download that download the image onto the HPC, and then you use Singularity execute command to run that container, and that will be how you run your application. So yeah, there's a Singularity pull command that just takes a URI of the location of the container image on a repository, and then the Singularity execute command to run a command inside a container. So you might say, I have some container and these commands will be run inside that container. But we can go into that during the examples. And there's also, Singularity will also store a cache or like just a local small database of the stuff you download. And so you can just clean that every now and then if you want to. It would just say, if you're downloading the same container a bunch of times, it'll speed up download processes, but it's just saved in your home directory, and you can say Singularity clean, cache clean, or Singularity cache list, and that will show you how much data you have, basically, for the how much space you're taking up with those containers. But generally, they are pretty lightweight. Okay, so to start with, I helped Alfonso, I think he's here, with a process with getting RStan to work on the HPC recently, which sort of inspired me to give this talk. So I have some other examples, but I thought I might just start with this one because it is a like useful little starting point, an introduction to containers. So he was having trouble with a compiler version installing RStan on the HPC. So we used a container basically to install software that needed. So I have a small post here that basically goes through the stuff, and I can share these links in the chat somewhere. Yes. So I have the chat here now as well. Cool. So basically all the examples I'll go through follow just some small posts so you can always come back to them if you need to like go through more details. The details will be in those posts, but yeah, basically we'll just go through and do this. So one thing I just want to show you first as well is I'm going to connect to the HPC using VS Code. So I also have a post about doing this, but basically you open VS Code, you install the remote SSH extension, and that will give you this little icon on the side here, which allows you to add SSH targets. So you could say you type in your SSH username at Zodiac HPC, and then that will give you a way to connect to the HPC using an IDE, basically. So then it's an integrated developer environment. It means you can upload and download files by dragging and dropping them. And you get a text editor. So for example, I can open my home directory. Yeah, so this is now my home directory on the HPC. So for example, yes, there's like the bash RC file on the directory. Oh, a better way to show it is if I open a terminal. So this terminal is on the HPC now. So if I type host name, I get ln2. So that's that login node to that I was talking about in the HPC structure. So this is on the HPC basically. And so if you wanted to change login nodes, you can just SSH to login node 1, and that will take you to the other login node. Host name. So now I'm on login node 1. It's probably not advisable to do that because they are load balanced. So there's a reason you get put on one or the other. It's generally because the load balancer says there's less demand on one node. So it's better to just stay in your node. Okay, so to start with, we're going to do this example for RStan. So I made a file and some code already on here, so that's a bit easier to use. So I have a containers directory. That's RStan. And so at any point, you can just type code and then a full stop, and that will open that directory in like a new window, and that will set like the working folder to that directory. So I have this RStan example. And so to start with, I'm just going to open another terminal. Just going to take this here so I can copy the text easily. Okay, so we have this RStan folder, which just has a couple of files in it. I'll just remove some of them actually. So basically, I just have a PBS script and an R script to run this stuff. But for whatever reason, RStan isn't installed or doesn't compile properly on the HPC. So we need our own version of RStan. So you can do that by pulling container that contains RStan already. So if I open a new window here, and I'm just going to type in, I already know this repository exists, but you could just search for one on Docker Hub or on Key.io, like I said. And so basically this is on Docker Hub. This is the sort of overview of the image. And so it just says installs R packages, RStan and Loo, and it builds from the Rockerverse. So the way that these containers work is they sort of build on top of each other, starting from an operating system, they build up. And so Rockerverse is the R containers. And so they have a bunch for Tidyverse and RStudio and different aspects of R. But yeah, so this is basically building on top of it. And I can show you the Docker file is basically a recipe. There's a recipe file for singularities, but for singularity containers, but singularity containers can also read Docker files. It's just saying from Rockerverse latest. So it's saying take the latest version of Rockerverse, and then it does some updating. It installs RStan. It sets some configuration, and then it runs an install process. So this is basically tells you what it's doing to build this stuff. And it's building inside Rockerverse. It's going to load. Yeah. So yeah, Rockerverse has a R instance, an RStudio instance, and Tidyverse instance. So it has a bunch of images, sorry, it has a bunch of different images. And so each one of these images will be built on top of another image, right? So it's like this one builds from tidyverse. And so they go all the way down, and eventually you'll get to an operating system like Ubuntu or Alpine or something like this. So they sort of build up from an operating system to an application. You can always build on top of these. So that's basically what's happening in this one. RSAN is getting built on top of our environment, basically, an R image. So to get this, all you need to do, because it's on Docker Hub, you just have to add a little thing to the start that just says docker : // So if I go back here, you can do Singularity pull docker : and then RSAN. So basically this is saying, tell Singularity to pull this image. And since I've already downloaded it before, like I was saying with the cache, it will like allow you to download stuff faster. So it's just using the caching. If I hadn't downloaded it previously and cached it, it would take a little while. You'd see it build a couple of layers, like it would build up each individual layer from the base operating system, the base image, up through Docker, up through RStudio, and until it built this layer as well. It doesn't take that long. It's fairly straightforward. It might just take a second to load this. So while that's loading, we can look at the file that I have. So basically, so I have this very simple script. It just requests some 4 CPUs and 8 gigs of memory for 30 minutes. And so Kevin wants to know, so is the code currently making the container into an object called RSAN? Yeah, so it's making a image file. So these are it's going to make a stan a CIF file, so an RSAN latest CIF file. So it's going to make this file, which is basically a binary image that executes, that can be used to execute code. So it's like the packaged container, and you can run that container or run that image. Yeah. So yeah, so it's just finished. It took a little while actually. So it has to convert it. So it downloads the blobs and then it converts them into a Singularity container. It takes a few minutes, but you only have to do that once. And so now I have this RSAN latest file. And so basically what we're going to do is use that command execute to run, execute this command rscript RSAN in this container. I might just show you quickly in the container, Singularity shell. So you can use a shell command. So now I get this Singularity prompt. And so that means I'm actually inside the container. So, so it's essentially a different operating system. I can run R and I don't need to type module load R, because it's already installed inside this container and it's separated. So it's in this like binary blob. So I can exit out of this container. And so now I'm back outside the container in my directory. One thing it does do actually is it binds the current directory into the container. So the file system you're working on in the container is actually your file system, your home directory from where you start the container. So you'll end up with a, make it bigger for you guys. So you'll end up, so I'm actually still in the same directory, and if I do pwd, I still get that /home. Well, yeah, I get this home / container / RSAN. So it mounts my home directory in the root of the container. So I still get that same, but it's actually all the software and stuff around it. The file system is the same, it's mounted in there, but the applications are separated. So it's slightly tricky to get your head around. But yeah, basically the containers come mounted with your home directory as one of the directories that are mounted inside them, just for Singularity containers. For other containers, you have to do that yourself. The thing with Singularity containers is that they can't be edited once they're created. That's part of the safety features of them, so that you can't modify them after they're already created. The percent is just a sorry, it's just a prompt for my shell. If I exit out of here, so it's just because I'm using ZSH. So so it's just because I have this PS1 command set there, so I can delete that. So yeah, well, it's actually still there now, but it was just that command, the prompt command. Can you change directories and containers? Yeah, you can change directories. So it's all the whole. So if I change to my home directory, the whole home directory is mounted in there. There's a couple of other directories. No, you don't need to use Visual Studio Code to access the containers. There it is. Sorry, here's a so this is just a terminal, the container, and I'll go to the same file, Singularity shell stand latest, and so yeah, I'm in the Singularity shell in a terminal. It's just a bit nicer way to work with containers because you can access and edit files as well, which is the main reason. So yeah, looking at this file, so we could change stuff in this file pretty easily, and it will get saved back onto the HPC. Same with this. So this is basically just a small command that does a linear regression using rstan. It just generates some data. Using this like linear model, and then defines a model in rstan to estimate these parameters, alpha, beta, sigma of the model, builds a model, and then samples from the posterior and prints it out and prints out a plot as well. So to run that, we just have to qsub the command, this qsub PBS rstan file. So this is to submit, qsubmit to the to the compute nodes. So that will start to run on the nodes, and pretty soon it'll give us some sort of output. So, yeah, so it's running. The job name is rstan. It'll take a little second to run, but yeah. Yeah, exactly. So you can also, Singularity containers are not purpose-built for Bayesian statistics. You're allowed to run whatever mode of stats you want on them. They are, yeah, belief independent. So this will run. It might just take a second to run. What am I doing? But once that completes, it will basically produce an output file. It just has to compile the model, so it'll take a little bit.
Hey, Wytamma.
Yep.
In terms of the file system, this is essentially just one file, right? It's just the image, and that's it.
Yeah. So the container is just this RStan and CIF file. Yeah. There are it does
Thanks.
cache some of it does cache some of the layers basically that are used to build it. Sorry. Yeah. So it does save some of those, but like I said, you can just use the clean command to remove those. So yeah, I have 9 container files. The total space used is like 3 gigs. So you can just go and type Singularity cache clean, and that will remove all those files. But basically, they're only stored in that place. Like they're just cached there. And then the Singularity image, the CIF file, Singularity image format is the only other file. So with Docker, it's a bit harder to maintain that stuff because they're all sort of stored in a repository on your local space. So you sort of have to manage it through saying Docker images or Docker containers to look at what's running and what images you have. But this one is just literally the file. So if you're done with the container, you can just delete that file, and that will be it. Yeah. Is that what you mean in terms of hey, yeah?
Yeah, that's super good because you know that I don't know if this is a practice that is advisable. I mean, but people does it right that they install Conda, and they create their own Conda environments. And in terms of the number of files that those environments create, that's huge.
Yeah,
and this is super good. It's just one file, and the system manages everything.
Yeah, exactly.
That's amazing.
Yeah. It's just one binary file, which is good. So yeah,
is this Wayne approved?
It is, yeah. So Wayne installed Singularity on the HPC to allow. I think they used it for the GPU stuff. So the GPU nodes, they use the base callers use Nextflow, which I'll show in this next little tutorial once this is done.
Yeah, I use that. It worked pretty well with the base call.
Right, yeah. So Nextflow can use Singularity containers to sort of package up all its workflows into a single platform. But yeah, so if I just refresh this, we get some output. We get good output. Here we go. So yeah, this is the model output. So it's pretty crazy output because it has to build the model. But right down the bottom does the sampling, and that you can see that the beta value has a mean of around 0.5, which is the same as the value that I used to generate the data. So good, it works. So yeah, that's just a simple example how you would use that to, so now you can run RStan and you don't have to sort of worry about the dependency issue. So how much should we be doing for time? Okay, so I might just show this one last one, and I was going to show an RStudio example, but I've shown that before. So I might just show this other pipeline example. So yeah, we've done that, and so the next thing I want to talk about is this Bioinformatics pipeline. So it's a quantification pipeline using Salmon for RNA-seq data. It's based on this Nextflow pipeline, but it's not using Nextflow. You could use Nextflow to do it, but I'm just pulling it the same process, but just taking it out of Nextflow just to make it a little bit simpler to understand. And so it uses these particular pieces of software, which so you could specify any versions that you wanted in here using containers. And it's based on, I'll share these slides around afterwards, but it's based on this workshop for containers, containerizing a pipeline. So if I close this, And I'll just go back to, I have this repository for that workshop downloaded. So I'll open that one. So there's an exercises file. So I have to quickly download this stuff because I didn't realize it would take too long. But I'm just going to pull these images first. Change. So yeah, basically the pipeline is going to do it's going to process some genomic data and then generate some quality reports, basically. So go here. Cool. So I just typed in that incorrectly. It came up with that warning, but yeah, so it's basically just going to download, do the same thing, download that image. I'm just going to do that a couple of times, just so I have all the images. It looks like it's actually working a bit faster. You already pulled that one. Sorry, I deleted these so I could show them downloading, but it's probably doesn't really matter that much. I bet I downloaded this in the wrong place. So just copy this one. Okay, so have all those images. And so basically this is the original pipeline. Hide this. This is the original pipeline from this workshop. And so basically it just sort of assumes that you already have Salmon, Fast QC and Multi QC all installed. And so it just goes through this pipeline, creates an index, does the quantification. It doesn't really matter what it's doing. Like the main point is that we're going to change this so that it can run in containers, as opposed to like using the software that's on the HPC. We're going to use software that's in containers. So if I go to this pipeline, so this is the same pipeline. However, now I'm defining the images, salmon image, up here. And so this is saying this is where the image I just downloaded is. So the container that I just downloaded can be found here. And basically I swapped out the single calls to that with a Singularity execute and then salmon inside it. So you add this little part to the front of the command that you would call. And so basically instead of executing looking for salmon in your path, it will run it inside the container. And so since that container contains salmon, it'll execute that and it will mount it like it's mounted to your current directory. So this should all run fairly nicely. And then just to turn that into a PBS script, I cleaned it up a little bit more with the working directory. So I just used the PBS working directory. So that's the current working directory from where you submit the job. And so it's just saying, yeah, you can find this image in this current working directory. And then same thing, Singularity execute that image. And then, so it's going to perform, it's exactly the same. It's just added as the original script. So as your original, like basically to convert from from a script that you already have, right? It says salmon to a pipeline using containers. You just have to add this sort of extra little bit to it to point to the container that you want to use. So this will just basically run the same way as the other one. You can just open a bash command, bash terminal, and so the containers are all here, and so we can test that they work by running Singularity. Yeah, so we can just do like the help command or something like that inside these containers. I just run multi-qc -- help. And then we get the output. So that is running inside the container, right? Like I never had the module load that or anything like that. It's just running inside that binary file. And so now if we qsub this bash pipeline, which sort of does the same thing, requests some time, some CPUs in memory, but uses the containers instead of those, instead of looking for the applications on the HPC. So we can submit that. Hope it didn't fail immediately. No, it looks like it didn't. Yeah, so that job will run, and the output will end up in this directory as well. So while that is running, I'll just take a look at this other sort of example that you can improve this even further by creating these sort of wrapper files. So instead of having that thing up the top that's like, this is the direction, this is the path to the image that I want to run, you can create a separate file that might be, okay, this is my fast QC image. And basically it has a path to that image. It has a command and it takes some arguments, and this file basically calls the Singularity execute command on some image with some command and some arguments. So this @ means the arguments passed to this fast QC file. So if I I need to just change directory into I'll just hard code this for a second because I think I don't have that variable set. So massive long file, but so now if I just run bash, you can make this executable, I guess, but bash qc and then say help. No, it says this new. Oh, yeah, I doubled up here a little bit. So I just typed the wrong path in because I copied and pasted it. It's never good. So there, so then I get the fast QC output. So now I have a fast QC file, and so I can even modify that so it becomes an executable. User plus executable plus QC. So now I can just say /fast QC, and so there, that's the failed output. But if I type help, I'll get the file does not exist in the container. Maybe that does not work. Oh, I wrote help wrong. Okay, So yeah, we get the help output for FastQC. So that's sort of a way to wrap up those containers a little bit nicer. So then you can end up, basically, you would add your path. You would add your path to say like, oh, this is where my wrappers are, that wrapper file. You just add that to your path. And then you go back to the same pipeline you started with. You don't even need the Singularity execute commands anymore, because these are all the wrapper commands basically. So where it says fastqc here, it will just run this file, which runs the Singularity command. So it's a way of sort of wrapping it up. So once you can sort of do that, you don't even actually have to modify your pipelines at all. Well, you do. You just have to say, this is my path. Basically, you don't even need that command really. The path is just saying this is where to look for executable files. And so you're just saying, well, I have these wrappers. And so now when it looks for salmon, it will look in the path and it will find salmon in those wrapper files. So it's sort of a nice way to package up containers into like a single command, so that now you you can basically just run your command as you normally would, but you are sort of in control of the software management now at this point. You can just install the container version that you want, and then create one of these little simple wrappers, and it will execute that command. You can just leave it as this as well if you don't want to go, if you're only sort of doing it simple way, you could just say Singularity execute image, and that will work fine as well. But if it's a file that you're using a lot, you can create this wrapper, and then to edit the version of the wrapper, you would just change the path to the image file, right? So I'll just pull a different image and point to that path basically. So is everyone okay with that? We have like 8 minutes left, so I'm happy to do like questions now, or I can go through. I have like one more RStudio example, but I think most of you guys have probably seen that one already. But if not, I can just push forward quickly. Where's the image coming from? So it is from Docker Hub. So when you use the pull command, it pulls it from the repository. So to go back, the registry repository is filled with these images, and when you use a pull command, it pulls it down to your computer, and then you run it as a container. So their key IO via containers. So there are just a bunch of biocontainers that are sort of managed. It's kind of like the CIF file is the image. Yeah, exactly. It stands for Singularity Image Format. So there are a bunch of biocontainers which basically contain all the bioinformatic tools, and you can they're all maintained on here. Let's see if this will work. But basically you can search for whatever tools you want, and they'll come up. Also, other things are in here, like if you want a GDAL, you can find that, and you can there are more, so sometimes you might have to look at one of these commands and say like, okay, how is this actually getting built? And so a lot of them are on GitHub, so you can sort of go to the GitHub and look at the build recipe to see like how it's getting built. But all these images are generally freely available. It's sort of another step to go through building and writing an image file yourself. But if you want to do that, I suggest you just look at the docs, or we can talk about it at another time maybe. But most software is just available in these containers in package up. So the last thing I was just going to show again is like using containers to run RStudio server on the HPC, which is the same sort of thing. You just RStudio server is like the RStudio application, but it's just running as a web service instead of like the application, so you can run it on the web. It's the reason that RStudio Cloud works. So this is RStudio Cloud. I don't know if everyone's used it, but it's basically a web version of RStudio where you can get projects and run RStudio on the cloud. And so you can do the same sort of thing from the HPC. So to show that example, I'll just use this while it's loading in the background. So I can share a link that says how to set this up, but basically I submit this start RStudio command to QSub, which will then give me a log file from today, Monday, it's today. It says run this command in my terminal. So I open a new window, which is basically just saying create a it's saying create a SSH tunnel back to my computer, and then gives me this local host that I can sign into. And so this is RStudio running on the compute nodes of the HPC. So if you can see here, this is my JC number, and then compute node number 1. So like the host name is compute node number 1. It's because it's running inside the HPC on like the actual compute nodes. And so this is very useful for doing interactive programming, obviously. So now you can use the full resources of the HPC. I could, for example, request. So if I look at, so I requested 4 CPUs and 8 gigs of RAM. And, if I was doing something more intensive, I could request more RAM than I need to work interactively. But yeah, it's just basically, it's using an RStudio container. So right at the very bottom of this, it says Singularity execute, and it has this path to the RStudio container, and then send some variables to that. It's a script that's set up, which I have a link to, which is in these slides, and I can share it as well. The same link here. But yeah, so it's just basically another way of using containers so that you get your own managed instance of, you're managing it yourself, of RStudio running on the HPC. So this is on the HPC, this is paid for, well, it's not paid, these are free, but you only get a certain amount of RAM and storage and number of projects before you have to pay, whereas you can just spin up your own RStudio, which you could then access from an iPad or whatever, wherever you are. So it's fairly useful for doing stuff like that. I think we're like right on the end of time. So if anyone has any questions, happy to answer them. Otherwise, each one of these sort of examples has associated guides to them, so you can always come back to it and look at it. But cool. Thank you.
Hey, Wytamma. Cool stuff.
Yeah.
So you use Singularity on the HPC, but you're saying you use Docker on your own computer?
Yeah, I have used Singularity, but I just tend to use Docker just because I'm more used to it, but they can use the same files. So generally I would write all the recipe files as a Docker format, just because everything can basically read, it's like the common format. So everything can read Docker pretty much. And then you can just use that with your Singularity stuff. So,
and sort of like, is it more for, I suppose it's like writing like really reproducible code, because like it's just one image for whatever whatever programs you're using. But
Yeah.
would you use multiple programs within the one container, or
Generally,
separate them?
Yeah, generally the idea is one application per container, and you sort of
Okay.
get them to talk to each other.
Yeah.
You can definitely break that rule. I think it's bendable. It's not like a set rule. It's just a matter of like portability and things like this. And
Yeah.
but it becomes a little bit harder to manage when they're all in separate containers.
Okay.
But
Yeah, I suppose for when you're on the HPC, is it more for if the program doesn't exist there, or you want a more updated version, or a legacy version?
Yeah, exactly. I would just, if you wanted something that wasn't there, you could use this together. For whatever reason, if it was broken, or if it was out of date, something like that.
Yeah, I suppose there's one of the things so I use this software Filucci for UCE analysis, and it only runs on Anaconda 2, and I think Wayne wants to get rid of Anaconda 2. So I might look at using it through Singularity instead. I just found there are recipes for it on Docker, so that's kind of cool. Yeah,
exactly. Yeah, so you can just use that and sort of even sidestep Anaconda as well, because Anaconda is basically a package manager, so you can just use the software directly.
Okay, cool. Thanks.
Okay. Well, sorry. Let's.
Thanks so much, Wytamma. That was fantastic, man. Thank you.
No worries. Yeah. Hopefully, it can help in a way. But yeah. Thanks, everyone.